So let's take a look at each one of the limiting cases that we talked about already and see what kind of kinetics they would have. So in one case, I could have something like chloropropane, and a hydroxide comes in at the exact same time that the chlorine leaves to make my product. So now, it's a concerted reaction. It's a single step. So then if I want to write the rate equation for this reaction, the rate equals K, or the rate constant, times any reactants that are involved in the rate determining step. Since there is only one step, that has to be the rate determining step. So it'll be rate equals K times the concentration of the alkyl halide times the concentration of hydroxide, because they're both involved in the rate determining step. The rate determining step of this reaction has two molecules involved in it. So if we're going to name this reaction, we'll say it's a substitution. And the substitution is occurring through a nucleophile, so it's a substitution nucleophilic. And then, since there are two molecules involved in the rate determining step, it's substitution nucleophilic bimolecular. And we'll abbreviate that as SN2. We do a capital S, a capital N as a subscript, and then 2. Substitution nucleophilic bimolecular. If I look at the rate equation is second order overall. It's first order in my alkyl halide. And it's first order in my nucleophile. Then the other limiting case is the case where the bond to the halogen breaks first and makes an intermediate. The intermediate then reacts with the nucleophile to give the product. And if you remember from the previous discussion, the rate determining step is the first one, the one where the neutral molecule breaks apart into two charged species, makes this carbocation, and there's a chloride minus. So if that's my rate determining step, my rate equals K, the rate constant, times the concentration of the alkyl halide only, because the hydroxide is not involved in the rate determining step. So if I look at this one, it's a substitution. And it's also being substituted by a nucleophile. But the rate determining step only has one molecule involved, so it would be unimolecular. Or abbreviated SN1. My rate law for the reaction is going to be first order overall. It's going to be first order in the alkyl halide. And it'll be 0th order in the nucleophile. So now you should try to pause the video and see if you can draw a reaction coordinate diagram for each of these reactions. Remember, this first one is a concerted reaction, while the second one is a stepwise reaction. So go ahead and try to draw the reaction coordinate diagrams, and then come back and I'll talk about it. Okay, so this first one being a concerted reaction, there's no intermediate in it, so it should go directly from reactants to products. The products should be more stable than the reactants, as one of the products is chloride, one of the reactants is hydroxide. And you can look at pKa's to determine that. So this is what you should see for a reaction coordinate diagram for an SN2 mechanism. Again, the rate equation for that, rate equals K times the concentration of the alkyl halide times the concentration of the nucleophile. The first step is the hardest one. We'll make an intermediate, and then we'll go to the products. The difference in the reactants and products in both reactions should be identical, delta H, because we have the same starting materials and the same products. It's only the way that we get there that's different. So in this case, because there's an intermediate, here I've got an intermediate formed, and this is a stepwise reaction. So this one is the SN1. So we're going to write the rate law for this again. Rate equals K times only the alkyl halide.